All right, in this problem, we're going to be asked to calculate the partial pressure of an individual gas in a mixture of gases. We recall the equation for the partial pressure of a gas in a mixture of gases. It's the mole fraction of that component times the total pressure. We note that we're given a value for the total pressure of the gas, so we're trying to find a means for calculating the mole fraction of carbon monoxide. The mix of gases that we're interested in result from a reaction of solid carbon with oxygen gas to give us carbon monoxide and carbon dioxide gases. So we're going to use a BCA table to determine how much we have of each reagent and product at the end. Our first task will be to identify which of the reagents is our limiting reagent. Will it be carbon or oxygen? So I'm going to pick carbon and test to see how much oxygen we will need to react it completely. All right, so here we show our calculation determining our limiting reagent. We start with our amount of carbon, and we use our mole-to-mole ratio to determine how much oxygen we need to consume all of that carbon. We see that we require 0.13 moles of O2. Okay, we have 0.3 moles, so we have plenty of O2, more than enough to react with the carbon. Therefore, we know that carbon is going to be our limiting reagent. It'll be completely consumed, and oxygen is our excess reagent. Okay, and now we note that our final mix is going to contain oxygen gas. It's left over. Remember, it's in excess. So it's going to have oxygen gas in addition to having carbon monoxide and CO2 gas. So we'll complete our BCA table, again, before, change, after. So we'll know how many moles of gas we have in the final mixture, and from that we can calculate the mole fraction of CO. All right, so here we are with our BCA table. Our limiting reagent is going to be completely consumed. So at the end, we know we're going to have no moles of that. Therefore, we know that we're going to lose 0.2 moles of carbon. We're going to use our change in limiting reagent to find out how much of our excess reagent we lose and how much we gain of our two products. So we reproduce the amount of our limiting reagent, and it's going to be multiplied in each case by some mole ratio. The ratio is obtained from the limiting reagent and the coefficient of the entity we're looking at. Now the factor here is obtained from the limiting reagent. The coefficient of the limiting reagent is in the denominator in each case. The numerator comes from the coefficient of the entity we're interested in. So that tells us how much we lose of this excess reagent and how much we gain of each of the products. Now to find the amount left at the end after, we add what we have at the beginning plus the change. Okay, so we've added to the before column, to the B, we've added the change, and we now have our values for how much we have of each reactant and product at the end. And we see that we have amounts of 3 different gases. We have some of the O2 that's left over. We've produced some carbon monoxide and some carbon dioxide. So all of these are the gases that we need to add together to find the total moles of gas in our final mixture. All right, so here we've totaled the number of moles of gases we have in the end mixture. We're going to have to cut off, looking at our sig figs, we're going to cut off our sig figs in the tenths column. So now we can finally go back to our original equation. We have the means to calculate our mole fraction, And we know that we have our value of P total, so now we can finally find our answer. All right, so here we are at the final answer. We've taken our definition of partial pressure, calculated the mole fraction of the component we're interested in, the carbon monoxide, and mole fraction is the moles of carbon monoxide over the total number of moles of gas, and we've multiplied by our total pressure. We can only justify 2 sig figs in our answer, so we rounded off to 2 sig figs.